Hello, welcome back. Looking at radioactive decay, and there's 4 types of radioactive decay. Most commonly, there's just these 2, and then there's energy that comes off of it called gamma radiation. So I'm just going to kind of quickly go over these 4 types of radiation. So radioactive decay is basically when the atom's nucleus is falling apart. So anytime there's a nuclear change, right? So in the nucleus you have protons and you have neutrons, right? So we got maybe some protons here, and let's draw our neutrons in a different color. Neutrons in a different color. If I change any of these proton numbers, if I remove a proton, add a proton, whatever it is, if that number of protons changes, it's called radioactive decay. And so there's several ways it can change. One of the most common ways is alpha decay. So alpha decay is where the nucleus itself actually loses 4 total particles, which is 2 protons right here and 2 neutrons. So we would say that alpha decay is a helium atom. And so what happens is a helium atom will definitely fling off of there. So it's got the 4. So it's got a mass of 4. So here's an example right here for alpha decay. Uranium-238 is right there. It's going to undergo alpha decay. So it's going to go down from 238 to 234 and turn into thorium. So why does it turn into thorium? Because it's lost 2 protons, taking it down on the chart from 92 to 90. So there's alpha decay. We can have beta decay. Now, beta decay is where the nucleus actually loses a high-energy electron type thing, which we call a beta particle. So it's charged negatively. One of the classic examples of beta decay is carbon-14. Carbon-14 will decay into nitrogen by losing a beta particle. So if we see what happens here, the beta particle flings off, and what beta decay does is it actually changes one of the neutrons into a proton. Now there's no mass here, so there's no mass change. So I go from 14 to 14. I'm only working with what was originally here. See, to start we had 8 neutrons and 6 protons, which is what gave us our total of 14. After the beta decay, I changed one of those 8 neutrons into a proton, so now I have 7 protons, which changes my atom to nitrogen. Now, beta can also sort of take the form of positron decay. So if it's positron decay, it's the same sort of thing that flings off of it, the same sort of particle, except it's got a slight positive charge. So it's kind of like an electron with a positive charge, and it does the opposite. So let's take a look at an example here. So here we have boron. This is not another beta, this is a boron. So boron has a total of 8 in its mass, which means it's going to have 5 protons and 3 neutrons. So if I go ahead and do positron decay, what I'm going to do is I'm going to turn one of those protons into a neutron. So I haven't changed my total mass number because I still have a total of 8. But now I have, because of the positron decay, I have 4 protons and 4 neutrons. So they're kind of opposite of each other, but they're very similar. So we got beta, where we change a proton into a neutron, positron, where we change a neutron into a proton. Actually, I said that exactly opposite. So we have this, you can see what it is right here. So just realize I just said it exactly opposite when I did that. There's also another kind of interesting type of decay called electron capture. So in electron capture, the nucleus can actually bring into itself a electron, actually pull the electron all the way into the nucleus. And when it does this, so here we have fluorine right here. When fluorine pulls that electron into the nucleus, it'll actually change, it'll actually combine with one of the protons essentially and cancel it out. So it'll change one of those protons to a neutron, which is kind of similar to what the positron does. So when you bring the positron in here, you see we changed a proton into a neutron. And the same with electron capture. They do the same kind of thing. And then also with any of this comes high energy. So the energy is called or nuclear or is called gamma. So nuclear energy is called gamma, and gamma is just written. You got 0, 0, and kind of a Y. So no mass, no charge. It's just energy, and so this is super high energy, very, very, very small wavelength, high frequency. And it penetrates through, through everything, very dangerous and all that. So gamma is always going to be associated with any of these charges. All right. So another thing to kind of think about with radioactive decay is the idea of half-life, right? So half-life is pretty easy to figure out and calculate. Let's say that they told you that you had a sample that started off at 120 grams, and then the half-life of it was 3 years. Okay, so if the half-life of that was 3 years, then in 3 years we would have 60 grams, right? And then in another 3 years we have 30 grams. So that would be at 6 years. Sorry, 30, not 36. Sorry, this is 3 years. So this is where we start. And so on and so forth from there. So at 9 years, we'd be down to 15 grams. So this is the idea of half-life. So every half-life, the thing has decayed half of the amount more. So it loses less and less for every half-life. But that's a pretty simple one to calculate or figure out. So, and this is always a first-order half-life for nuclear decay. Is always a first-order decay. There's a couple other things that are kind of interesting associated with this. We could kind of go ahead and put some trends up here. So as far as nuclear decay goes, the smaller a atom is, the less likely it is to fall apart, right? So let's say that if an isotope has a mass number, and the mass number is greater than its atomic weight, then the nucleus will try to gain protons and lose neutrons. So therefore, if the mass number is greater than its atomic weight, you can expect beta decay. So anytime we have like a total, like let's say that carbon-14 is a good example. So the atomic weight of carbon-14, or carbon, is typically So like in carbon-14 here, you see that, so say you were given this isotope, you look at the periodic table and you'll find that mass is somewhere around 12. Well, notice this is bigger. So if I'm asking you about this isotope, what's this isotope most likely going to do? Well, what's most likely it's going to do is it's going to want to add to this number to kind of make those even. So it's going to try to get some kind of beta decay going on where it can increase. And sure enough, it turns into nitrogen, right? And so that's kind of the trend that you would expect. If the number of the isotope is greater than what you see on the periodic table, then you can expect beta decay. You can expect those proton numbers to try to increase. If it's less, like say I said, what would happen to carbon-11? I don't think it exists, but let's just say, what happened to carbon-11? Well, then you'd look at the periodic table and you say, oh, look at that, it's less than this weight of this isotope is less than what I see on the periodic table. And so this thing's going to try to lose protons and turn into something else. Like it might try to turn into, boron. It might try to turn into boron instead, right? So it's going to try to kind of keep things evenly spread like this. And so there's a way to predict that. Now, what about alpha, you'd say? So like I said, if it's very, very small, it's not likely to decay. And so if it is going to decay, you're going to have some kind of beta or some kind of positron. So in this one, we did a positron. In this one, we did a beta. For alpha, you're talking about big, old, huge atoms that can fall apart easily. So anytime you get an atomic number greater than 60, you could just say, you know, if it's greater than 60, it's probably going to have some kind of alpha decay. All right. So that's kind of a trick to figuring out what sort of decay is most likely to happen to an atom if they just ask you to look at the periodic table and figure it out.